So today our topic is classification models, and we have to understand KNN for the day. So our KNN algorithm, it is called as distance based machine learning algorithm. So the abbreviation here KNN stands for K nearest neighbor, and this falls under supervised machine learning algorithm. Okay, the good thing is that you can solve it for classification and also for numeric prediction, which is regression. So it's that, we often observe that we share many characteristics same as our peers, right? We have friends where people are similarly thinking, right, at the workplace, or many factors you take. After that, what we do, if at all we find your peer friends who are near to us, we build friendship with people who are similar to us. The same principle KNN also employs here. Okay, KNN also does the same thing here. Okay, so its aim is to locate the closest neighbors. Okay, the aim is to locate the closest neighbors, and around an unknown data point, unknown observation, who is close to this unknown observation, that is what you have to do. It is a straightforward, and it is very much easy for any person to find out, to identify a person who is close to me. But how this KNN does is it tries to calculate distance, okay, from all the points, tries to calculate the distance from all the points of unknown data and filters out those people. If this is a new data point and you have, these are the people, and these are few other people. So what does KNN do here? KNN tries to calculate the distance from this unknown data to this, unknown data to this, unknown data to this, all the other data points who are near to it, and that is the distance calculation what we are doing. So it is filters out based on who is near to me, based on who is near to me. If at all you are having a scenario where you have to segregate this question mark to a class which is this, or which is a tick mark. So what will you do? You just go and calculate the distance from this data point to the in the circle, the distance calculated which is near. Whichever is having the shortest distance, whichever is very, very near. Near means you calculate distance, which is the shortest distance, okay, to it. It is a class you are going to categorize. If you see this distance is less when compared to this distance. So this question mark will be replaced with a tick mark. It will become a tick mark class. Okay. If at all you are having a star mark here, this is very, very near. So the question mark will go and understand that this is a classifier. This will become the classified output. So the entire story revolves around the distance based algorithm. It's all about the distance. So in order to correctly classify the results, we must determine something which is called as your K value. Your K value is something what you have to decide. Okay, whether it is image classification, whether it is handwriting classification, whether it is a person is a good customer or bad customer, he's a risky customer or not, whether it's a loan defaulter or not, right? Whether his credit history is, you can give him approve him a loan or not. All these scenarios are calculated, can be done, can be solved. Business problems can be solved using this KNN. So it is a classifier, and the other name is that it is a lazy learner. It is a supervised learning model. If at all you want to predict a numeric value, you use KNN regressor. If at all you are having a non-numeric value, you use KNN classifier. So KNN algorithm, it will store the data, it will fix to the which category you want, all will revolve around your K value only. But it works the best for classification rather than it works for regression. Okay, it works for regression. So how do you calculate the distance is a point. You can use any distance calculation which are available. Like you may have to go for the best and the preferred one is Euclidean distance, or you can go for Manhattan distance or Mahalanobis distance calculations can be done here. Okay, and you are the actually initial days when I explained you, there is something called as, if you are choosing your K value, okay, as 3, you got the classifier and you try to calculate the accuracy. Because here, what is a label, you know it. If Y is known, you have to concentrate on accuracy of your model. For instance, if K is equal to 3 is what you have built model 1, you have predicted, your model has predicted with an accuracy of 80%, but 80% accuracy, the client is not happy with that. What we will do? We have to come back and you have to tune the parameter and change the K value. The only parameter which you have in your hands to change. This is called as the tuning parameter. K itself is a tuning parameter. Okay, whenever the problem statement is of classification type, it will take a call on if you are using a classifier, you are using a KNN classifier using for classification, your KNN takes a concept which is called as a majority voting. Majority voting. Within your given range of K, the class with the most votes, majority votes is chosen. More votes is chosen. So if at all you have two different people here, if at all you have two different people and here and there you have the star marks, okay, and here you have diamond shape. Okay, we have few diamonds here. Now suddenly a question mark came into picture. This is a new data point. Okay. Now what happens? You will decide that your K value should be equal to 5. You said that K is equal to 5. Okay, there is a star mark and there is a diamond. Now, what is that you will focus here is you want the 5 neighbors which are near to this. Okay, which are near. 5 neighbors is what it is required. 5 neighbors out of which maybe you get, see, 1, 2, 3, 4, and this is 5. It takes like this. So out of which you have 4 diamonds and you have 1 star. Now this question mark is a diamond or star. Means he is a good customer or a bad customer. The transaction is a fraud or not fraud. Right? His loan status, his loan status is approved or it is not. Anything you can take which is a classifier, which is the classifier. So you can say that these are good customers, these are risky customers. Now this is question mark will relate to good or risky customer. Okay, now if you see this concept, now 4 people are good customers with this question mark and 1 is bad customer, risky customer. So if you take this question mark, will go and sit in good. Why? It takes call on majority. It takes call on majority. Right? It relates with majority concept. Okay, so what is that you can change here? The thing what you can change here from your end is only the K value. It's only the K value. This is how it calculates. So if you look at to this, there's a question mark and you have 2-class problem. It's a 2-class problem. So for multi-class classification, we have different algorithms, but for binary classifier, KNN is the good. Okay, now new example to classify this question mark. You calculate the distance from this to all the nearest data points. How many data points you want? That is something what you take. It is nothing but if your K is equal to 1, K equal to 2, K equal to 3, that many people's distance you calculate. That many people's distance you calculate. That's where finding neighbors and you are trying to vote for the labels. That K equal to 3. So 3 are, if you have 3 stars or if you have 3 diamonds, if there is an ambiguity situation, first it will focus on majority. If there is ambiguity, it will go with shortest distance calculation. It goes with shortest distance calculation. That is how your KNN is going to work. So where we are using this, if at all you want to go and do loan approval, given the inputs of a person, given the inputs, you have to approve a loan. For that, then you can say you want to approve or disapprove a loan. Using a KNN classification, you can do that. Right? If at all you are using bank's risk management or you want to measure the performance of the bank, if you want to measure the performance of the bank, then that also is done using a regression. Performance is good or bad is a classifier. Risk is associated or no risk. Risk there or risk not there. That is again a classifier. Right? If at all you want to predict the scoring assessment of a person, customer, you are able to do with KNN classifier. You want to predict whether it is a fraud transaction or not fraud transaction, then also it is a application of KNN. So when we talk about KNN, any classifier instance, it's any classifier you take. That classifier is you use multiple classifiers, right? But that classifier which gives you the good output is your final prediction model. Okay, that is your final prediction model. So let's not waste time and understand this in our Jupyter notebook. That is Google Colab. Okay, today our contest is to predict loan eligibility prediction. This is a use case. Now it is a risk of loss resulting from the failure by a borrower to repay the principal and interest. So the lender, he uses the interest payments from the loan to compensate the risk of your potential losses. So when the borrower defaults on his or her obligations, it will be an interruption in the cash flow of the lender. So it's very, very important factor in the bank sector that before you approve the loan of any customer, right, we have to know the loss of the cash flow and you reduce the severity of the losses. The data what we have collected here is loan ID, that is the unique loan ID, which is a nominal data. The applicant is a male or a female, okay, whether married or not married, how many dependents are there, she completed her graduation or not, he or she, is it self-employed or not, what is the income of the applicant, if at all you have any co-applicants, what is his income in case of a joint loan, loan amount term of loan months, whether the applicant's credit history meets the required guidelines or not, the area, the property pertaining to the loan, it belongs to urban or semi-urban or rural, and loan status. You have to approve, loan not approved. So given these details of a person, you should decide whether the loan is approved or not. You have built a prediction model, you have collected the historic data. So I have collected the data here, I have loaded it, loan eligibility data set. Here, let us understand. So now what is that we should do first? We want few things in hand. First thing is we are building on daily basis. We want pandas, we want numpy as NP, we want matplotlib.pyplot as PLT, we want cborn as SNS. Either matplotlib, which is a normal visualization, cborn, which is an advanced visualization. And remember, one point is very, very important here, friends. Whenever you have all the data collected, all the features collected, if at all it is numeric data, and the underlying concept or the context of how your machine learns the patterns is a distance calculation. So KNN by name itself, we are saying it is a distance based algorithm. So you are calculating distance. So you need to scale your data. What is that scale? Scale is nothing but you are doing a kind of pre-processing. We are doing a kind of pre-processing where whatever might be the range of your columns, range of features, whatever be the range of features, all should come and stay in one range. The minimum value and the maximum value should be in the same range. That is 0 to 1, or if you apply normalization, okay, normalization, there is a formula for this. It takes x minus minimum of x by max of x minus minimum of x. If you do this, all the data points, whatever which are here in our data, if they are numeric, income, co-applicant's income, loan amount, these are numeric. And they are of different ranges. If you see here, all have to come into the same range. So you apply normalization, and that is available in sklearn pre-processing, importing standard scalar. Now the question is, earlier, yesterday's session, we did not do any splitting because there is no need to check any cross validation can be done because it is unsupervised learning algorithm, and whenever It's unsupervised. Whatever you get, you accept it. Whatever the algorithm gives, you accept it. If you accept it, right, there is no particular metric to check whether it is good or bad. Whatever it gives, yes, it is there. Okay, now what is it we are doing? We will split our data. When I have to validate my data, when it is supervised learning model, this is my entire data. I split my data into train and test. I asked to learn the patterns on, build the model on train data. I'll pass this output of the model. I pass my test data and check how well it is performing on the train data. So whatever data, however split I want to make, standard rule is a 70-30 ratio or 80-20 ratio, where this will go for training, this will go for testing. Whatever accuracy you get, you generalize it and you report it in the project charter, saying that this is the accuracy of your model. This is the accuracy of your model. Okay, so what is it which is more important here is when we are splitting it, okay, it could be a random split. So I have used sklearn.model_selection. I'm asking to import train test split. Okay, and I am also importing from neighbors KNC. The shortcut nickname also I can give. It is KNC or K nearest neighbor. Okay, now the point is, how will you evaluate your model is good or bad? If it is a classifier, right, it is a classifier. Now the prediction happens in categorical form. The output what you are getting is yes or no, right? Yes or no. Now how can you calculate accuracy of this model? If your predicted value is yes and the actual value is no, okay, how can you calculate error for such data? How can you calculate error for such data? There comes here the evaluation metric. Okay, the evaluation metric here is called as crosstab or confusion matrix. Okay, this is nothing but it is a binary contingency table. Okay, it is a binary contingency table. It takes like this: actual values, predicted values. Two cases are there: yes and no, yes and no, approved or rejected. How many cases are actually yes and your model has predicted yes? How many cases are actually no, your model has predicted no? Right? These are errors. Actual value is not equal to predicted value. Both the scenarios are not. The cross marks are this. How do you now find out the accuracy of such models? Yes, yes scenario less no, no scenario by total. Okay, this is your accuracy of your model. You want to calculate error of your model? Yes. This cross mark plus cross mark by total, error plus error by total will give me the error. This output is available in matrix in sklearn. Confusion matrix is a function or crosstab, whatever. Pandas is having crosstab. This is having this. If at all you have any warnings, you are saying please ignore those warnings. This is a data set what I have. Loan ID, gender, married or not, dependents, education, self-employed, etc. etc. Loan status, yes or no. So what is yes or no here? Approved 1 is yes, 0 not approved is 0. Okay, So that is nothing but I have loaded the data set now. I just copied the path and I saved that entire thing. pd._csv here. Okay, you paste the path, whatever you have copied. Head will give me the first 5 observations, 0, 1, 2, 3, 4. 5 observations it is going to give. Inform is going to give me how many are object, how many are categorical, how many are integer type, and how many are float type of data. So my data is very, very small data set is what I have taken, where I have 614 observations and 13 columns. Where I have numeric data types are 4. 4, I think. Applicant's income, co-applicant's income, loan amount underscore term, credit history, and loan status. The rest of the variables, whatever you have here, they're object. Okay, now if at all you see that here, loan ID, it is an identifier, and there are several columns with less than 614 non-null entries. These columns are having total is 614. Here 601. Here again 611. 3 missing values are there. 614 minus 599. Null values are there. So education, no null values. 582, 614. Null values are there. If all are 614, it is no null values. But here if you see, most of them are not 614. Here and there null values are there. But most of the null values are available in credit history. So we have to even tweak that. We have to do pre-processing for that. Okay, now 614 are the data points what I have. Okay, what we have to do is we have to start pre-processing. First thing is, if you observe this loan ID is a numeric data. It is nominal. And just like, you have an ID. We used to have roll number in our school, right? It is an ID. Like when you register, when you submit your application form or anything, you get one acknowledged ID. That is the ID what you have. I need not work with that, so I dropped it. What happened? Okay, it's already deleted, right? So it's showing me an error. No problem. So now when you do this, we are taking columns. Okay, what are the numeric columns here? These are the numeric columns. I am doing describe on top of it. Okay, I am doing describe. So describe function will give me a 5-number summary. It is giving me the mean. It is giving me standard deviation of all the numeric data. If you observe here, $5403 is the mean of the applicant's income. The minimum value here is 150. It is very, very small. 5403 and minimum. Why are you doing describe function? To check whether your data should do normalization or not. Should do normalization or not. So maybe that 150 could be an outlier because there's a lot of they're far away from your mean and median. There are a good number of co-applicants. Let's see, with no income. Right? If you see here, even 25% of your data, whatever you have collected, they are having income as 0. Now comes here, we have to do some kind of feature engineering. According to principle of parsimony, Occam's-razor has given you a statement that how simple your model is, that much better is your model. Right? You have simpler the model, better is the model. So according to the concept of principle of parsimony, better the model. What is that you should do here is, you should do some kind of feature engineering to reduce the number of columns. You can add them, you can subtract them, you can multiply them, you can apply log, you can make division, anything you want, you can apply so that you can reduce the features. Okay, so what is that I'm doing? I'm converting the entire scale of loan term, which is there, from months to years I have done to make it easy. Then I have added the total. This total income is what new column I have created in data. and I have added applicant's income and co-applicant's income, which is giving me total income. So I'm going to data set, go to this income plus go to this income. Sorry, 1 minute. So what is it you are getting here? You are getting total income. So when I got a new variable, I fetched a new variable, I can delete these two. In place is equal to true will replace my data in the original data set also. Okay, now I can check another pre-processing which is required is outliers, skewness, distribution of the data. So now we have only two columns. One is loan amount, one is total income. So I have written for two columns, for loop is what I have written. So for it is iterating only for 2 times, I have used a for loop. Okay, I'm asking it to print the column name. I'm asking it to print what is the skewness. Okay, for this column loan amount, calculate the skewness, and I'm making it please is saying that plot a histogram with 10 bins, and also you plot a box plot for the column. So if you observe here, for same loan amount, I got skewness as 2.68, and I can see some outliers here. So one plot, what am I doing is histogram, right? One plot I am doing here is box plot. Two plots, two different plots I'm getting. Skewness is 5.63. Oh my God. See, if at all you are understanding the distribution here, it is like this. Here also, if you observe, the distribution happens to be like this. Very, very long tail. So many outliers are there. So both the variables are having so many outliers this side. So data is containing different, what is understanding? They have different types of areas. People who are from rural, urban, semi-urban, they are applying for the loans. So we can observe that majority of the values of the total income, they are less than this $10,000. Okay. So what we can do now, we have to work with categorical variables now. Most of them are categorical only. Gender, married, dependents, education, self-employed, credit history, property area, loan status. Loan status is your output column. Rest of them are your input column. So there's a function which is called as value underscore counts. Okay. What am I writing? Call in this categorical column, this column, go for each and every column, go to gender, calculate value underscore counts. Okay, calculate value underscore counts. This will give me how many male are there, male percentage people are there, how many female percentage people are there. Again, you go to every particular married column. How many people are married, not married? So married people are more, not married people are very, very less. Dependents, right? 0 dependents, 1 dependent, 2 dependent, more than 3 dependents. This is a percentage. This is a proportion of people falling in that particular range. Educated, not educated, that is graduate or not graduate. 2. So most of the people are graduates only here. Self-employed people, no, not self-employed. Yes is only 14%. Who are having the credit history? If you see here, 1 which is 84% people are having credit history, and 0.15% are having no credit history. According to the property area, many people who are applying for loans, they have the property. Most of them are semi-urban and urban. And you can see the proportions are likely like nearly equal, 37, 32, 29. They are nearly equal. Finally, loan status, approved people are more, not approved people are very, very less. This is a proportion calculations, what we have done for categorical data. To give an idea that how many people are male or female, how many are dependents, how many are graduates, how many have submitted the property related to semi-urban and urban, all these things we are finding. So see, this is an observation what we could do. 57% of them have no dependents only. 78% are graduates, 85% are self-employed, 84% of the applicants have credit histories. That is going to where it is. See here. Where is our credit history? Gender, married, dependent, self-employed, credit history, 84%. Right? The property area among the applicants is roughly evenly split, but semi-urban is more. 37% is a semi-urban. Now, as the first info function we have seen there, you could observe that, see, total data is 614, but 601, 599, 614, they are not, none of them are matching with 614. If 614 and 614 are equal, means no missing values. But 582, 614 minus 582, you have some missing values in your data. So you have to go for imputation technique to do that. So if at all it is a categorical data, I impute using mode. How do I do that? For all the columns which are categorical in nature, I am saying go to data, every column, every COL. So COL will go to gender. It will fill NA value. Okay, how it is going to fill the NA value? It is going to calculate that particular column's mode. Okay, so mode will be in 0th index. Generally, mode will be in 0th index. Take that value, it is 0 or 1. Take that, take the most repeated value, fill in. Okay, if you have anything to replace, now if at all it is numeric data, okay, we have not done outlier treatment, no? So we will do imputation with median. Okay, so because you have any null values, empty spaces are there, first you have filled them, you can replace them with 0. Whatever zeros are there, you replace them with np.nan. After that, the same loan amount, np.nan is filled with the median value. If you cross check now, all the columns null values are solved. Okay, what is our loan status here? It is yes or no. So that is not understood. You want 1 or 0, we replace. So we are asking, we are replacing all your n with 0 and all your y with 1. It is a key and a value pair. It's a dictionary. So loan status, n is replaced with 0, y is replaced with 1. So now we have completed our data pre-processing. But now what is it we should see is, whatever numeric data we have here, is it having good relationship among themselves, and is it good to take all the inputs for prediction? So if you observe here, I'm trying to find out the relationship between loan amount with the total income. So what is the inference you're getting from this? The loan amount and total income, everything is going in linear, right? So this implies that the loan amount for higher income applicants, it is higher only. But if you see here, there are few people who are outliers, out of scope people. 1, 2, these are out of scope. So what is the inference you get here? These are with low income, right? They have been given a loan of higher amount. So with low income group people, we are giving a higher amount. Similarly, if you take loan status with the total income, right? See, these are the people here who are where we have the outliers here. So what is the observation? Except leaving 1 or 2 outliers, there is no difference between income of, see, till here. If I draw a line like this, right? 1, 2, 3. These are outliers. Other than that, the income of customers who are eligible versus those who are not, there is no much difference here, status. So the income alone might not be a good indicator. We are saying that income is not a correct attribute to check loan eligibility, because if you remove these 3 outliers, both are same. So income is not a major factor to find out this or this is to give them loan or not. Similarly, you can check with credit history also. So I have used a box plot, I have used a count plot, different plots to understand relationship between the variables. To understand relationship between the variables means I'm doing a kind of feature engineering. I'm doing a kind of feature engineering here. Okay, so if you see here, credit history, and this is the count, right? Count. It is a count plot. So it is giving how many people. Blue color is 0 and orange color is 1 with the credit history. So what is the inferences from this? This shows that credit history is very, very important factor while checking the loan eligibility. The few customers whose loan was approved, very few customers. Okay, the few customers where the credit history, it did not meet the guidelines, still they have got loan approved. There are few people. So like that, when you keep on checking with education and how this is impacting your loan status. See, we can see that graduate customers are more, they are getting loans. Non-graduate customers, they are not getting loans. Now we can also check with the property area and loan status. All are equally good, right? More loans are approved only for semi-urban people. But this could be of several reasons, right? Maybe the bank is charging more interest rates for suburban areas. Or maybe these are more eligible for home loans based on this features of the loan applicant. We cannot take a call just by looking at the plots also. Now it is time for model building. So model cannot take non-numeric inputs. First, we have to create dummy variables for all the categorical variables. Okay, so first I'll divide my x and y and I create my x, all the dummy variables. Okay, all the dummies are created. Then I split my data. So I first splitted x and y, and for x I've created dummies. Then I'm using train test split data, x and y, with a test size 30. So this entire data set is divided into like this. This is 70% of the data. This is 30% of the data. Right? Now the evaluation metric here. Right? The evaluation metric here is that confusion matrix, which I have explained you just now. So when you are drawing a contingency table like this, okay, yes or no, predicted value, actual value, yes or no. Now you are going to say this is true positives. You are saying that loan is approved, your model is also saying loan is approved. You are saying that loan is rejected, your model is also saying loan is rejected. Right? If the actual value is no, actually you are saying loan not taken, not given, loan is not approved. But your predicted value is saying yes, loan is approved. Right? If you at all loan is not approved, but it is telling loan is approved. Here it is again an opposite scenario. Actual value, you are saying yes. Predicted value, you are saying no. So you are predicting the customer when which case is more important is what you are trying to check. So predicting a customer is not eligible for loan when the customer is actually eligible. It is loss of opportunity. Predicting a customer is eligible for loan when the customer is actually not. It is a financial loss. So he is eligible, right? He is not eligible. He is eligible. Actually, he is not eligible. You are telling your model is predicting that he is eligible. Right? I repeat, when your actual value your model is predicting, the predicted value is telling the customer is eligible. Yes is eligible. But actual value is no. When this is happening, what is the scenario now? Predicted value is yes, actually this is loss of opportunity. Actually, the customer is eligible. Okay, we have written ulta now. This is here. Right? Actually, it is yes, but the predicted value, actually it is no. Okay, this opposite is this one. Actually, it is eligible. Predicted value is telling not eligible. Two scenarios are there. So when the customer is actually eligible, when a customer is eligible, your model is saying no. This is loss of opportunity. This is your financial loss. Now tell me, both are errors only. Which one is more important? Which is more loss? Financial loss is more dangerous because he is not actually perfect person to take the loan, but your model is saying yes, because he may default on the loan and he may not be able to return the loan, which would be a financial loss to the company, which might be a financial loss to the company, loss to the bank. So to reduce this scenario is called as false negative. This is false positive. Right? So we are saying a cost-based analytics where how much is the loss? Based on that, you decide whether you have to reduce your false positives or you have to reduce your false negatives. So here the scenario is you are predicting the customer is who is eligible when he is not. So actually he is not eligible, but your model is saying you are predicting that he is eligible for the loan. It means he will not pay on time. He will become a defaulter eventually, which is a loss. Occurrence of loss is something. So you have to reduce this. How to reduce this loss? You want to decrease that false negative values. Okay, that is the aim here. So let us understand now KNN and check how are our false negatives here. So what am I doing here? I just gave, I want 11 nearest neighbor. My K is 11. Okay. And I'm fitting my data. I'm predicting here. Okay. Now what is it I do? This is my trained data. I pass this data to KNN model. Whatever output is coming, I take the test data. Output of the model, I pass my test data, I get the predictions. So this KNN.predict, I'm passing my test data, I got the predictions. Okay, now I have to measure accuracy of my model, how well my model could, I could run on test data. So what did I do? Whatever predictions I got and whatever original data I have, I passed it here. Then I passed my cross tab confusion matrix, original data and predicted data, which will help me to know how many false negative values are there. This is one set. As I told you, when you are sending your kit for test, you are not only testing on test data, you are also testing on train data also. How well your training happened, that also you are checking. So you are checking your X-train here and also you are checking your predicted value. So you get accuracy score, right? You're also getting, this is my test accuracy, this is my train accuracy. So this is how I got it. This is my actual value, this is my predicted value, 0, 1, 0 and 1. So this is who are not eligible, not eligible. Who are eligible, this is also eligible. Okay, your model is saying 17 people are not eligible. Your actual also predicted value, both are equal, 17. Both are correct. You are saying eligible people as eligible. Now errors came here. errors are here. Eligible people, they are eligible. You are telling them they are not eligible. Okay, actually they are not eligible, but your predicted value is telling they are eligible. These two are errors. So what you can do is to reduce the dangerous problem and you want to improve the accuracy of the model, you have only one weapon in your hands to change the k value. So what we can do, we have run k for different values, k equal to 1, k equal to 2, k equal to 3, k equal to 4, like 20 models you are building. You are asking it to train. See, I becomes 1, it will fit your data, it will predict, it will give you the train accuracy. Again, it will predict on test data, it will compare, it will just give the test accuracy. Finally, you are adding train accuracy and test accuracy. Whichever is giving you better accuracy with less false negative values, that one you will take. Right? I got it. Now, if at all you want to check AACC, see for different values of k, you got the accuracies. K equal to 1, k equal to 2, k equal to 3, k equal to 4, 5, 6, 7, 8, like this. Okay, now if at all you want to see now k equal to 1, 2, 3, 4, 5, 6, 7. See, this is what we have done for 11. Now we can try with k equal to 12 also. So what you can do is you will do a plot. We will take all train accuracies in red color, test accuracies in blue color. So we want to get a better model. So this is good enough. See here, 11 or 12. In between these two you have here, this distance is very, very less. From here, anything you can take. Here, if you see, this is my train accuracy. This is my test accuracy. The difference between both of them should be minimal. Train accuracy should be nearly equal to test accuracy. If at all you want to run it for n number, right? Now you can come here, you can change it into 12, right? Because or 21, anything, 20, you will have to run it. Right? See here. Your accuracies are changing. 2 to 3%, 5% acceptance is good. But the bad thing here is you should have a dangerous scenario is there, no? That should be reduced. Actually, not eligible people, predicted values, not eligible, eligible. 13, 118, 290, and 8. Okay. One is those are eligible. If I'm not wrong, what did we do here? How did we change our label? Status, somewhere we have changed the labels. Just give me a second. 0 and 1. So according to the confusion matrix, your aim is to reduce those people, those metrics. So loss of opportunity or financial loss? Financial loss is more dangerous. So predicting a customer is eligible for loan, you are telling he is eligible when he is not eligible. These are 118 cases. See, you are telling he is eligible. Prediction is telling he is eligible. When he is not eligible, 118 people you are telling, your model is telling 118 people are worse people. They are not up to the mark people. So maybe you have to change. You have to go with distance. So because of this, this is called as, it's a non-parametric algorithm and it is also called as a lazy learner. when you call any algorithm as a lazy learner, it is that it is not learning any math equations from any pattern learning is not happening. You give the data, it is giving you the output based on a distance calculation. No, nothing is happening here. It is something which is happened. It's a memory based learning. Directly take it, give the output. Take the data, give the output. It is not learning any patterns. And one of the thing is only K is something which you have in your hand as a tuning parameter. Right? And we are very happy to announce you guys that we are having a Python themed Python session starting from 11 July. Right? Please subscribe to our channel and you can avail the videos pertaining to Python, where the lectures are being conducted by the experts here. So from 11 July, we are having sessions in the evening. Right? It is 6:30 to 7:30. Right? So that's it, friends. This is a supervised learning algorithm, which is a classification model. Thank you.